Hello, class. So on this video, we're going to continue on section 6.1, where we introduce the Laplace transform. All right, so in the previous video, we introduced the definition. Right? It's basically this improper integral. So the Laplace transform of a function f of t, which is real valued, meaning that the range is the real numbers, and that is defined for t greater than or equal to 0. Right? At least it could be defined for values of t less than 0, but for us, it doesn't matter since the improper integral only goes from 0 to infinity. We're not considering negative values of t. So as long as you have that, then you can define this Laplace transform, right, as of f of t as the integral from 0 to infinity of f of t multiplied by e to the negative st, right, where s is just some constant for us. Why is it a constant? Because we're evaluating the integral with respect to t. Now, as we saw in the previous video, the Laplace transform doesn't always exist because, as we know from Calc 2, an improper integral doesn't always converge. Right? It's a limit. The limit might not exist, which means that we have to be careful about how we apply the Laplace transform. Right? But if it exists, right, since we're evaluating or integrating with respect to t, and we're plugging in 0 and b in the integral, if this limit converges, what we're left with is some expression involving the variable s, which was a constant for us in terms of the integration. Okay? And that's what I wrote here, underlined in red. Right? As the Laplace transform of f of t equals f of s, assuming that the Laplace transform exists. And as I mentioned, we're going to use lowercase letters for functions and then corresponding uppercase letters for the Laplace transform of a function. Okay. So that was the previous video. Now let's actually go ahead and do some examples. Let's try computing these things. Okay. So find the following. Laplace transform of 1, of t, of e to the 5t, and sine of 2t. Okay. So let's do the first few. So we want to find the Laplace transform. Laplace transform of 1. So by definition, this is the integral from 0 to infinity of e to the negative st times the function 1. In our case, f of t is 1, dt. Then by definition, every time you're computing this by hand, the first thing you want to do is write this as a limit. This is the limit as b approaches infinity of the integral of 0 to b. E to the negative st times 1 is just e to the negative st dt. Now we can actually go ahead and simplify. Remember that s, for our purposes, even though it's a variable, since we're integrating with respect to t, for the purpose of integration, it's a constant. Okay. So what is this going to be? We need an antiderivative. Well, an antiderivative of e to the negative st is negative 1 over s e to the negative st, right? Because remember that negative s is a constant for us. It's just using the power rule for exponentials. And we evaluate this from 0 to b. Right, so what do we get? So plug in everything. And then notice that I'm leaving the limit till the end. And that's what you want to do. You want to leave the limit as the last thing you evaluate. Okay, so let's evaluate this. We get negative 1 over s, e to the negative s, plug in b for t, right? Minus, now we plug in 0 for t, so negative 1 over s, e to the negative s times 0. One more simplification, then I think we can evaluate the limit. So we get negative 1 over s, e to the negative sb, minus and minus becomes plus, so plus 1 over s times e to the negative s times 0, right? Any number times 0 is just 0. E to the 0 is 1. Now let's evaluate the limit. Well, what's the limit as b approaches infinity of this? Well, if we assume that s is positive, then negative s times b is negative, right? Because remember that b is taken as going from 0 to infinity, right? So at least it's non-negative. Right? So again, assuming s is positive, minus sb is negative, and as b goes to infinity, that means that the exponential is getting, the exponent of the exponential is getting larger in the negative direction. Another way of looking at this, which might be simpler, so let me do one more simplification to the negative 1 over s times 1 over e to the sb. Let's write it like that. So again, if s is positive, since b is positive, as b grows larger, this fraction here is going to 0, which means that this whole product is going to 0. And 1 over s is a constant, right, for the purpose of the limit, which means that the only thing that's left over is 1 over s. Again, assuming that s is greater than 0. If s is less than 0, this is not the case anymore, because this part here is not necessarily going to go to 0. Okay, so the Laplace transform of 1 is 1 over s, assuming that s is greater than 0. Right? And as you see here, we started with a function of t, even though it's a constant. Right? You're going to see with the next example how the variable t vanishes. But either way, we started with a function of t, and we ended with a function of s. And in fact, in this case, we know what the domain is. Right? We know that s has to be greater than 0. Right? So this is just a function 1 over s, where s is greater than 0. But you can graph that in the f of s point, right? Where s is the horizontal axis and f of s is the vertical axis, as usual. Okay, so this is one example. Let's do a more complicated one. Let's do L of t, the Laplace transform of t. This is part B. Laplace transform of t. Again, by definition, this is the integral from 0 to infinity. Oops, too many zeros. From 0 to infinity of e to the negative st times f, in our case f of st, dt. Again, as always, the first thing we want to do when evaluate this by hand is write this as the limit as b approaches infinity of the integral from 0 to b, and then leave the inside the same. But this is always the first step. You can skip this step if you want. I like to write it because that's the actual definition, but you can definitely skip to the second step. However, I would always write that this Laplace transform is equal to this limit before I do anything else. Right? That way it's clear for me as a grader, and it's also clear for you what you have to do. Right? Evaluate the inside first, at the end evaluate the limit. Okay, so let's go ahead and simplify. So again, we evaluate the inside first, and then we worry about the limit later. So this is e to the negative st times t. Right? So we're going to have to use integration by parts. So let's do that. We're going to let u be equal to t. So du equals dt. dv is going to be e to the negative st dt. So v is going to be negative 1 over s e to the negative st. So it's the usual integration by parts, which means that this integral becomes the limit as b approaches infinity of uv, right? So u is t, v is negative 1 over s e to the negative st, right? So uv, so t times negative 1 over s e to the negative st, evaluated from 0 to b. I'm going to need more space here. Minus the integral of v du, right? So negative 1 over s e to the negative st times du, which is just dt. Right, so I don't need that parentheses here. Okay, and then close bracket. So let's simplify. So now I'm just going to write equality because everything's going to be equal here. This is the limit as b approaches infinity of, okay, so plug in b, get b, and I'm going to simplify. So I'm simplifying this first term. So I'm simplifying this right now. All right, so plug in b and 0. So if I plug in b, what do I get? I get negative b over s, e to the negative s times b. Right. Then when we plug in 0, so minus, what happens when we plug in 0, but we're multiplying by t here. So we're going to be multiplying by 0 when we replace all t's by 0. Right, so that term goes to 0. Right. Let's do the second term now. Okay, so I have a, let me use another color. I have minus and minus, right, so it's going to be plus. Right, so plus integral from 0 to b. 1 over s is a constant for our purposes of integration because we're integrating with respect to t. I can move the constant outside, and we have e to the negative st dt. Now I'm going to change colors, and let's evaluate this integral, see what we get. So let's do that here in this space. So we have the integral from 0 to b of e to the negative st dt. Right. This is going to be negative 1 over s, e to the negative st. Right. That's an antiderivative. I'll let it from 0 to b. I think I'm going to need a little bit more space. Okay, so maybe one more line. So plugging b in 0, what do you get? Negative 1 over s, e to the negative sb, minus, now when you plug in 0, 1 over s, e to the negative s times 0. I'm going to need one more line. And then when you simplify, what do you get? You get negative 1 over s, e to the negative sb, minus is plus, e to the 0 is 1, so plus 1 over s. So that's just the part underlined in blue, right? That's just that integral. So let's go ahead and plug everything in. Right, so this part we already simplified. Plus 1 over s times this whole expression. Right, so if multiplied by 1 over s, we get 1 over s squared, e to the negative, oh, and there's a minus in front, sorry, so it should be a minus. Okay, so minus here and a plus there. Right, so minus 1 over s squared, e to the negative sb, and then plus 1 over s squared. Right, so all I did was multiply this thing here by 1 over s. Now take the limit as b approaches infinity. Right. Now what's going to happen here? As we saw before, if we assume that s is greater than 0, then we know that this term is going to 0, right, necessarily. So this will be going to 0, assuming that s is greater than 0. Right. Now what about this term here? Is it going to 0? Well, it's not necessarily obvious that it's going to 0. So it might be useful to think about what's going on there a little bit. So have the limit as b approaches infinity of, so let me rewrite it. So we can take the negative 1 over s outside because that's a constant with respect to the limit. And we're left with b over e to the sb. Again, assuming that s is greater than 0, what's going to happen? The denominator is getting larger and larger, but so is the numerator because b is approaching infinity. So how would you know what this limit is? Well, you could argue a few different ways. You could say that the growth rate of the exponential is way higher than the growth rate of just the function b. Right? So that would be one way to say, okay, this is going to be negative 1 over s times 0, which is 0. Another way would be to apply L'Hopital's rule. Right? So you either apply L'Hopital's rule from Calc 1 or Calc 2, I think Calc 1. Let me see if I don't misspell it. Or I should remember how to spell it. Or argue by growth rates. And again, that means that you're saying that the exponential grows a lot faster than the polynomial b, right? So the denominator is growing way faster than the numerator, so this is still going to 0, even though both the numerator and denominator are growing. So by that argument, this goes to 0. 1 over s squared is a constant for purposes of this limit, right? So this just ends up being, and let me use another number, ends up being another color. Let's use black. This ends up being just 1 over s squared, but again, we use the assumption that s is greater than 0 to evaluate these limits, right? So assuming that s is greater than 0. Right? So again, here, you can see that we start with a function of t. I started with t as a function of t, and we ended up with a function of s. And we, in fact, know what the domain of this function is because we have this restriction. We're saying, okay, s has to be greater than 0 for this Laplace transform to exist. Okay. So we get this polynomial, well, not polynomial, this function 1 over s squared with domain s greater than 0. Now, you can calculate the others as well. For sake of time, I'm just going to go on. But you can see the process, right? It's basically a Calc 2 exercise. That's all this is, calculating the Laplace transform. So the other two as an exercise. Let's leave that. Okay. So let's move on. Now, an important thing about L is that it is linear. So notice what L is doing. Right. Think of L, this operator L, as a function. Right. What is L doing? It's a function. No, actually, let me do it below so we have more space. So note, L is a function. If it's a function, we can talk about its domain and range. Right, so what's its domain? Well, if you look at the definition of the Laplace transform, we're looking for functions f of t defined for t greater than or equal to 0, right? And for which, if we want to look for just the domain for which the Laplace transform actually exists, then we're looking for functions f of t defined for t greater than or equal to 0, for which this integral converges, right? So that's the domain. So where am I? Here, okay. Domain is the set of all functions f of t for t greater than or equal to 0, right? Defined for t greater than or equal to 0. For which this integral converges. Right. So what does this mean? The domain of the Laplace as a transformation, as a function, is functions. Right. So it's a function whose domain is functions. Specifically, functions defined for t greater than or equal to 0, for which this improper integral converges. So what is the range? Well, the range is harder to describe, right? As you see, because, well, how do we know what the Laplace transform of a function is? Well, we don't know, but we can say a few things. For sure, just based on the notes I gave you previous videos, we know that the range are functions of S, right? Whatever they look like. Okay. Again, we know that because, as we saw before, if the Laplace transform of a function exists, it ends up being a function of x, just an expression involving the variable x. So, although we don't know exactly what the range looks like, we know that there are functions of s, whatever they look like. So, we can think of L as a function whose domain is this set of functions for which this integral converges and defined for t greater than or equal to 0, right? And the range is functions as well. Okay? Why am I going over all this? Well, I'm going over all this because L is a linear operator. Now, you went over this in the homework, right? I didn't explicitly say that this is what being linear is, but if you remember in one of the homeworks, you showed that this operator, just not curly L, not math calligraphy L, right, but just regular L, which was defined as this differential operator. So we did it in the case where we had two derivatives. So let's just write it like this. Plus a1 of x dx plus a naught, right? So if you remember, you did an example in the homework where you had to show that this function satisfied that L of f, or let me use y, I think we're using y's. So L of y1 plus y2 is the same as L of y1 plus L of y2. And you also have to verify that for any constant, L of c times y1 was the same as c times L of y1. Well, these two properties together are called the linearity property. So any function that satisfies these two properties is said to be linear. Right? So, for example, the derivative, just the derivative itself, is linear. Right? We know that from Calc 1, right? Because as you remember, let me add a page here. If you remember, we know that the derivative satisfies these conditions. Right? You know that dx of f plus g equals d dx of f plus d dx of g, assuming that the derivative exists, of course. Right, the derivatives exist. So let me just write, assuming that f prime and g prime exist. Right? And then similarly, you also know that if you have a constant times the derivative of a constant times a function, you can move that constant outside. Again, assuming that the derivative of f exists. Right? Or that f prime exists, right? It's the same thing, which implies that the derivative as a function is linear. Right? And what's the domain? Well, the domain of the derivative operator or function is functions whose derivative exists, right? And what's the output? Well, it's the derivatives, which again are functions. So this is another example of a function whose domain is functions and output is functions. Just like what we did with, just like the Laplace transform, right? We saw that the domain is functions of a particular kind, and the range or output is functions of a particular kind. Another example of a linear function or operator is the integral. So similar thing holds for integrals. So we do the integral of f plus g dt is the integral of f plus the integral of g, and the integral of a constant times f is constant times the integral of f dt. Again, assuming all integrals exist. Right? Which means, again, that the integral as a function, or let me just write it, and it works for both definite and indefinite integrals. So let me just say the integral, whether it's definite or indefinite, is linear, or is a linear function. Which again, what's the domain? Well, the domain is functions that are integrable. And what's the range or the outputs? Well, if it's definite integral, then the outputs are constants. If it's indefinite, then the outputs are functions again. So again, you have another example of a function, the integral, considered as a function whose domain is functions of a certain kind, right, the integrable ones, and whose output is either constants or functions that could not be constants necessarily. Don't necessarily have to be constants. Right? So this linearity property is actually more common than you think. Right? We use it all the time in Calc 1 and Calc 2 when working with derivatives and integrals. So similarly, we're going to use it when working with the Laplace transform as a function. And here I wrote that property of linearity just in one line. Right? The Laplace transform of a times f of t plus g times b times g of t, assuming that a and b are constants, right? And that f of t are defined for t greater than or equal to 0. And I should add, assuming that the Laplace transforms exist. So here, let me add, and that L of f, oh, not L like this, but calligraphy L of f and L of g exist, right? So assuming that and having a and b be constants, then the Laplace transform of a constant times f plus a constant times g, well, we can separate the sum, just like we do with derivatives and integral, and we can move the constants outside, just like we do with integrals. So what are we left with? And this is a typo here. Okay, so what are we left with? Well, we're left with a times the Laplace transform of f. We're assuming that it exists, right? So again, if you remember, the Laplace transform of a function we label as a capital letter. Right? So capital F of s plus b times the Laplace transform of g. We're assuming that it exists, right? So capital G of s. Right? What we're going to do is we're going to use this linearity property to evaluate the Laplace transform of more complicated functions. So function's more complicated than what we have here. Okay. So we're going to do that in the next video.